And here we are in College Algebra, Chapter 2, Section 6, where we're going to talk about combinations of functions and composite functions. And one of maybe the most important parts about working with a composite function is taking notice of the domain. Because not only do you have the domain of one function, if you're working with a composite function, now you might have a couple of domains that you need to take into consideration. Some of the most frequently worked with types of functions that we see as we build these composite functions are polynomial functions, like this one here. And the domain of a polynomial function is all real numbers. There are no restrictions on the values that you can plug into a polynomial function. The second function, g of x, that we see here is a rational function. And one of the key features of a rational function is that the variable is in the denominator. And the reason why that can get a little tricky is because the denominator of the function then has the opportunity to become 0, which we don't like. We don't like division by 0. It causes our function to be undefined, and in this case, an x value of -5 would cause our denominator to be 0. And to the right, we have a radical function. The square root function has a requirement that the radicand, which is the stuff under the square root symbol, this stuff, in this case the x plus 2, must be greater than or equal to 0. So again, the radicand must always be greater than or equal to 0. Because we can take the square root of 0, it's equal to 0. And the square root of a positive number, while it might give you an ugly decimal, you can still do it. Take the positive or the square root of a positive number. But in this particular point in our course, we don't want to be taking the square root of a negative. It would result in an imaginary number. So we would have to incorporate I, the imaginary unit, but we're not doing that at the moment. And here we have the algebra of functions. So this is in large part about notation, and it is okay to add two functions together, and so you might see that expressed as one function plus another function, or you might see it using this notation, f plus g of x. So the left-hand side of that statement, again, I would read it as f plus g of x, whereas the right-hand side, as you probably would naturally read it, is f of x plus g of x. Just realize that those two are equivalent. The second one introduces the difference, which is subtraction instead of addition. The third one is a product. And the fourth one is a quotient, but as happens with PDFs, sometimes an equal sign does not translate into the PDF, so make sure that this is an equal sign and this should be a does not equal sign. So if you're printing out this particular table, or if you're taking digital notes, make sure you do your best to scribble in the other half of those equal signs. In number 4, you'll see that there's this additional note that says provided g of x does not equal 0. So we're getting into the domain again. A rational function does not want to have a 0 in the denominator. And let's see how that plays out when we're working with some actual functions. So this example wants us to build all of our composite functions. So f plus g of x which is f of x plus g of x. So we've got our x plus 6, that's f of x, plus g of x, which is 5x squared. There isn't much to do with this other than maybe shuffle the order around. Typically we see the larger exponent term written first, so I would write the 5x squared and then plus the x to the first, and then plus our constant value of 6. Then let's subtract our functions. F minus g of x. So again, we have our first function, f of x, x plus 6, a minus sign this time, and then our 5x squared. Again, not a lot to do here, except for I would change the order, and that negative sign, or the minus sign, is changing or modifying the 5x squared. So I would write this as negative 5x squared plus x plus 6. Let's also do, let's switch colors again. Let's also do g minus f of x. Let's put our g function first, 5x squared, minus our f function, which is x plus 6. And you'll notice I keep using parentheses over and over again as I'm replacing the f with what the f function is and g with what g is. I'm putting those expressions in parentheses. And here, and the reason I did this is to really highlight this important step that you need to take, especially when it's a function minus another function, is we now have to distribute this minus sign to the two terms in that second function. So our resulting function would say 5x squared minus x minus 6. All right, that's not rocket science. This is nothing new that you have to distribute, but I want to point out the importance of using these parentheses, especially when it's coming after a minus sign. All right, let's keep going and look at the product of our functions. F times g of x. Our f function was the x plus 6. Our g function is the 5x squared. This is something that you don't run into very often. But you should know that you're allowed to distribute from the right. We do need to, we can, and we probably should, multiply this 5x squared into both of those terms in our function f. You should also know, well, I'll ask you, what's 3 times 2? You say 6. And then I say, what's 2 times 3? And you say, why, that's also 6. So 2 times 3 and 3 times 2, it doesn't matter that the order in which we write the factors that are being multiplied together. You can take that idea and extend it to this problem, or this example that we're looking at right here, and you could rewrite this as 5x squared times x plus 6, and now maybe it would be more intuitive to do the distribution. Oh, if I distribute from the left, it's going to give me the same result as distributing from the right. Sometimes the order of the terms might change around, but you know that once you've got it all as addition and subtraction, you can change the order as necessary. So whether we distribute from the right or from the left, our final expression here should say 5x to the third plus 30x squared. And then lastly, the quotient f over g, or f divided by g, of x. Now that's not times x, it says of x. X is our variable. It's not multiplication. Don't try to divide by this x right here. We've got x plus 6 being divided by 5x squared. It's not much of a square. There we go. Can we simplify this function at all? We could. I don't know exactly how much simpler it's going to look, but there is a bit of simplification that we could do. You could certainly leave this as a final answer, but just be aware that if it's a multiple choice situation, it could be So I'm going to put a box around this because this could be a final answer. Or we could distribute our division. There is, of course, a distributive property of multiplication. We just did that in the previous example for the product of our two functions. And I really wish I had been doing this in purple. I like having the different colors separating the different examples. So sorry about that. We could put maybe a purple line in here at least. We could distribute our division here and write the x as being divided by 5x squared plus the 6 being divided by 5x squared. And every once in a while we do need to do that in order to express a final answer in a particular format. But in this case it wouldn't be super typical, but if we did distribute our division, now we could reduce these x's and write that term as 1 over 5x, but our second term would not change. It would still be 6 over 5x squared. So this is another acceptable format for a final answer to building this composite function. Remember, please, you cannot reduce your x's over here. If you're going to do any reducing or simplifying, you must distribute the denominator to all of the terms in the numerator. That's what we did over here. This is okay. This is okay. This, not okay. So that is some function arithmetic, and it's not, I suppose you could call it function composition, but more typically, when we're working on function composition, we're seeing this kind of notation here, or this notation, which a lot of people call fog notation. These two are equivalent. I much prefer this notation right here, because I can more clearly see which function is being plugged into the other function. I can see which one's the inner and which one's the outer function. Anytime a problem is given to me using this format, the first thing I typically do is rewrite it using my preferred format. And then we see a little commentary about domain. The domain of the composite function f of g is the set of all x values such that x must be in the domain of g and g of x, which is the output value from the g function. All of those output values must be in the domain of f. So let's see an example where we get to inspect the domain of a composite function. This is, you've maybe seen some illustrations of what a function looks like. You see that we have an input value going in here into our function g, and then we have the output that is g of x. So g of x is an output value, and then that's dropping into this tube right here as an input value for the f function, and then finally we get the output from that f function, which is the result of having processed both functions. F of g of x would be the output of that composite function. Some of us like those diagrams. It helps to put a visual to these kind of abstract things like we're seeing on the screen now. So here are a couple of functions, and we're going to build these composites. We'll build f of g of x, we'll build g of f of x, and then we'll take the number 2 and actually plug it into f of g of x. Let's see what happens. So for part A, that's f of g of x, and of course I like to write it as f of g of x. So I'm going to go through and replace, first, I'm going to replace g of x with what it really is. So I'm going to write this as f of 2x squared minus 9. So you can see here that we're taking the g function and plugging it into our f function. All right, what's the result of that? Well, our function f says 7x plus 1. It's 7 times our input value, and then we add 1. So I'm going to take 7, and I'm going to multiply it by my input value, which is 2x squared minus 9. And then, after we do that multiplication, we're going to add 1. And the 1 that I'm adding right here is this plus 1 up here. So that's the entirety of my f function, my outer function. Not a bad idea, honestly, if you're using two different colored writing utensils, or if you have a highlighter that you want to use. Keeping track of where these numbers come from as they sort of appear somewhat magically in our work can be a little tricky. So highlighting different elements like that and making sure the colors match up might be helpful to you. From here, all you have to do is distribute and combine like terms, right? From here, it should be pretty straightforward. I'm going to wrap onto the next line just so I don't run out of space. I'll indent a little bit with my equal sign. I've got 14x squared. 7 times 9 is 63, so it's minus 63, and then we have to add the 1, and then we'll combine like terms. 14x squared minus 62. Let's do part C next. Part C, I will change colors this time. Part C says f of g of 2, which is the same thing as f of g of 2. You have options at this point because you know what f of g of x is. So you could take the 2 and you could plug it in for x right there. Square it, multiply it by 14, and subtract 62. Your other option is to keep f right here and then take 2 and plug it into your g function. So let's see, how should I do that with colors? Let's do our g function, which is 2 times our x value of 2, and we have to square that and then subtract 9. So this is probably the best way to do it, is to write down that this is g of 2. And then we can do those calculations. I've got 8 minus 9, which is negative 1, so this is equal to f of negative 1. Then we can take the negative 1 and plug it into our f function. So that is 7 times the negative 1 plus 1. And if you want to keep highlighting that plus 1, you're welcome to. I don't think you probably need to at this point, and that is negative 6. Let's make sure it works by plugging it into our already figured out composite function f of g of x. Let's see. Let's write that down here as, or you could use a different color perhaps. 14 times 2 squared minus 62, and that's equal to 14 times 4 minus 62, which equals 14 times 2 is 28 times 2 is 56, which does indeed equal negative 6. So you could do it either way. If you had not already, I don't know, which one of those do you think is faster? I don't know. They're pretty similar. Which one do you think is easier? Well, as long as you've got a calculator, they're both pretty easy. The thing that I liked about taking this root instead of this root is that in this root, we were working with smaller numbers. I started out with a 2 as an input value. I did some arithmetic in here, and that turned into a -1. Still a pretty small number. It was 8 minus 9. I can handle that kind of arithmetic. And then that value of -1 got plugged into my f function, and I'm working with, again, pretty small numbers here. Doing that in my head was a lot easier. If you take this root right here, the numbers are a little bit larger. You've got to subtract 62. I don't know. As long as you've got a calculator, I guess it doesn't much matter. Just clean that up a little bit. And lastly, let's build g of f of x. I'll use my notation, my preferred notation. It's not my notation. G of f of x, which is equal to g of what is my f function? 7x plus 1. And what am I going to do with the 7x plus 1? I'm going to square it and then multiply it by 2 and then subtract 9. So this is going to require some arithmetic. Here's 2 times the 7x plus 1 as our input value, squared minus 9. And then we're off to the races for some arithmetic. 7x plus 1 squared. So I'm going to keep the 2 on the outside, and then I'm going to FOIL and combine like terms all in one step. If you need to write out 7x plus 1 times 7x plus 1 and FOIL, and then in your next step combine like terms, you should do that. In fact, pause the video right now, write it out for yourself, and then after you have FOILed and combined like terms, check it against what I get. I got 49x squared plus 14x, that should be 7x plus 7x, plus 1, which is 1 times 1. And then don't forget to bring the minus 9 with you. So if you're sort of taking notes on the process as we're going along, you could put a little note that you're FOILing here in order to get down to the next line. And then as we go from here to the next step, we're going to distribute, D-I-S-T for distribute. That gives us 100 minus 2 is 98x squared. That's a lot of x squareds. Plus 28x plus 2, and there's the minus 9 still. And then lastly, we will combine like terms, CLT for combine like terms. Just the 2 minus the 9 is all we have to do now. 98x squared plus 28x minus 7. F of g of x and g of f of x are radically different from each other. You can see in red, in the red box toward the top of your screen is f of g of x, and at the bottom in blue is g of f of x. Very different expressions. Is it possible that f of g of x and g of f of x ever equal the same thing? If your two functions were identical, if f and g were the same function, then those two composite functions would be the same. Or if f of g, or if f and g are inverse functions, then the result of the composite functions will be the same. We'll get there. What else are we seeing? Excluding values from the domain of a composite function. If x isn't in the domain of your inner function g, then it must not be in the domain of your composite function. And any x value for which g of x is not in the domain. So if you took an x value, and you plugged it into your function g, you would get an output value, g of x. Of course, that output value is then going to be going into your f function. But if that output value is not acceptable as an input value into your f function, then you probably shouldn't put in that x value to begin with. So we have to be sensitive to the domain of g and of f. Let's see if we have an example where we can illustrate that. Two rational functions where the variable's in the denominator. So we've got to be careful here. Let's start out by finding the domain of f of g of x. We could even maybe, let's just put f of g of x, and then we'll put a colon. Note, for g of x, have a look at g of x. What x value don't we want to plug into the g of x function? We don't want to cause division by 0 in a rational function, so make sure you don't plug in an x value of 0 into your g of x function. So I'm going to put a note that says x is not allowed to equal 0. Maybe we could even circle it or highlight it or something. This is important. We don't want to lose track of this. This is going to be part of our final answer. The next thing I'm going to do is I'm going to build f of g of x. F of g of x equals f of 6 over x. Now I'm going to take 6 over x and plug it into my function f. So this equals 6 over x as an input value divided by 6 over x plus 5. So if you look, how should we do this? Have a look right here. See this x right here and this x right here? Those x's are being replaced by 6 over x. This 6 over x, which is this one, which is this one. So again, these x's in our f of x function are being replaced by 6 over x. All right, let's start tidying this up. There are actually a couple of different ways that we could go right now. One is we could make a common denominator down here in order to add these two expressions or these two values together. And once that's one big fraction, then we'll have a fraction divided by a fraction, and we could do keep, change, flip, and we could tidy this thing up like crazy. And then we could ask ourselves, are there any domain restrictions? We have another option. We already know that x is not allowed to equal 0. That would cause division by 0, there and there. The other place that we don't want to cause division is in this bigger denominator, 6x plus 5. So let's just take this and make sure, let's write another note that says 6 over x plus 5 is not allowed to equal 0, because that would cause division by 0 also. Let's figure out the x value that would cause this to happen, and then we will exclude it from our domain. I will subtract 5 from both sides so that we have 6 over x is not allowed to equal negative 5. And then I'm going to multiply both sides by x. so that 6 is not allowed to equal negative 5x. And then I'm going to divide both sides by negative 5, so that negative 6/5 is not allowed to equal x. This is the other value that we need to leave out of our domain. We don't want x to equal negative 6/5. If you don't believe me, try taking negative 6/5 and plugging it in as that denominator right there. And then when you do this addition, where you add the 5, I think you'll find that that big denominator becomes 0. Or you could just take my word for it, that you don't want x to equal negative 6/5. But this idea, the strategy, generally speaking, that you want to take with you is when you're working with a rational function, you don't want the denominator to equal 0. So we had our inner function, g of x. We made sure that that denominator did not end up equaling 0. And then we built our composite function, and then we checked to make sure that that larger denominator is not going to end up equaling 0. Now, it's not always going to be that you're going to take two rational functions and compose them together, like f of g of x. Sometimes it's going to be a rational function and a radical function with a square root in it. So there are different combinations. Just keep those very first restrictions that we talked about right at the beginning of this video. Keep those in mind. No division by 0 and no square rooting negative numbers. All right, let's write our final answer. What is the domain of f of g of x? It's all of the numbers except for 0 and negative 6/5. So that's everything from negative infinity up to negative 6/5, or that's the union symbol, or we can use, I don't know why I'm writing at an angle, I don't know why that happened, or we can use values that start from negative 6/5 going up to 0, but we don't want to include 0, or we can use values from 0 going all the way up to positive infinity. Remember that these parentheses mean that we're excluding the values that are right next to them. So the parenthesis here excludes the value of negative 6/5, excludes negative 6/5, excludes 0. So we are indeed leaving them out, even though those numbers are written there. And that is your solution in interval notation. That's your domain. The instructions said to find f of g of x. So we didn't really take that all the way. I kind of stopped right here because I was eager to get to the domain part of the conversation. Let's go ahead and finish sort of tidying up things in our construction of f of g of x. How should we make sure that our notes stay cohesive now that I've interrupted things by the domain? Let's Continue with f of g of x equals, we have 6 over x divided by 6 over x. And now I'm going to make a modification. I'm going to write this as plus 5 over 1, which is the same as 5, times x over x in order to achieve a common denominator. So if you have space in your notes, whether you're writing on the same kind of printed notes that I am, or if you're just on scratch paper, you could put a little note in here that says make common denominator, or maybe your bracket should go all the way across here, whatever's going to make most sense to you if and when you review your notes. This is equal to 6 over x, all divided by 6 plus 5x all over x. Because I have a common denominator down here now, This term has a denominator of x. This says 5x over x. They have the same denominator, so I can add my numerators together and write them all over my common denominator. Now what I'm looking at is a fraction divided by a fraction, which I really like having because it allows me to do keep, change, flip. Division is the same thing as multiplying by a fraction. And if you don't know that exceptionally well, that might be something you want to write down. Division is the same thing as multiplying by the reciprocal, which is what we're going to do. We're going to take the 6 over x, and instead of dividing it by that fraction, I'm going to multiply by the reciprocal of that fraction, x over 6 plus 5x. We can cross cancel, if that's how you call it. Those x's do cancel, and we're left with 6 over 6 plus 5x. And this is f of g of x. This denominator can't equal 0. The x value that would cause it to equal 0 is this one. If you plug that in for x, it would make that denominator equal to 0. But we've excluded it from the domain, so we're safe. So that's your function. That's your domain. It's a little bit of a mess. You might want to reprint that page and write it all out in a more cohesive order. You could do, let's see, if I were going to rewrite these notes, what would I write down? If I were going to rewrite them, I would write, let's see, how should I do this for you? Let's do this and this. I would write this down first, this line, and then I would write this stuff, I would write second, and then I would cut to here with an equal sign still, and I would write this stuff down, all of that, I would write third, and then I'd come back and start looking at the domain. And since you have to build f of g of x for this question anyway, you could then start your inspection of the domain from right here. You could put a note that says 6 plus 5x is not allowed to equal 0. And you could subtract 5x from both sides, or rather subtract 6 from both sides. 5x is not allowed to equal negative 6. Divide both sides by 5. X is not allowed to equal negative 6/5. In the bottom right-hand corner of your screen, x is not allowed to equal negative 6/5. In the top left-hand corner of your screen, same thing. So we can arrive at that same destination by a couple of different paths. I got there by sort of skewing off in the middle of the process, or you can build your entire composite function and then look for that other possible domain restriction. You'll get there either way. So this this last inspection that we did about the domain, I would do that fourth, or write that out fourth. Whew. I feel like I need to stand up and stretch or something. That was a very involved process. Let's do it in reverse. It was so great. Let's do it backwards. This is, instead of a composite function, now we're going to be decomposing functions. And you're welcome to read the text that's here. I'm going to move down and look right at an example problem. And the thing that I want to highlight for you here is that there are two things that are happening in a way, I think we could say. One thing that's happening in this function h of x is, and let's make that a little bigger and a little darker. There we go. In this function h of x, there are a couple of things happening. One thing that's happening is we're taking a square root. And we're taking the square root of something. And the thing that we're taking the square root of is 5x squared plus 3. Now if I asked you, which one of those two functions, the square rooting function or the 5x squared plus 3, which one of those two functions is inside the other one? Would you say that the square root function is inside of the 5x squared plus 3? I don't think that you would, especially visually, just looking at it. That square root symbol is almost like a roof or some kind of a shelter that's literally over the 5x squared plus 3. So I would tend to say the 5x squared plus 3 is inside of the square root function. So when you then go and you try to express this as a composite function, I think it's a good idea for the inner function, g of x, to be the 5x squared plus 3, and then I would let the outer function be the square root function. And then how do you denote that you've made that decision, that you've come to that conclusion about how to decompose this thing? You would write it like this. Since f is our outer function and it's doing the square rooting, you would declare that f of x equals the square root of x. And then that your inner function is the g function, which is the 5x squared plus 3. It's a little bit confusing, I think, because this says x instead of saying 5x squared plus 3. But don't worry, once you replace this x with a g of x, then you would have to also replace this x with a g of x, which is 5x squared plus 3. You would then have the square root of 5x squared plus 3, which takes you full circle all the way back to your h function, which is, there it is, f of g of x. It's almost fun. Almost. You just have to put yourself in the right state of mind in order to have it be a little bit fun. And even if it's not fun, it can be very gratifying, because if you get this process down, you're going to be getting lots of right answers, and that usually equates to higher marks, which we like also. Alright, that's it for composite functions. Thanks for hanging with me on that one. See you next time.